Good afternoon, sir.
Good afternoon, madam.
Yes, sir. Can we start, sir?
Yeah, are you guys ready?
Yes, sir. We are ready.
Sure, no problem.
Yes, sir. Yes, sir.
How many participants are there?
Yeah, actually, now we have already switched on the live streaming. We can see at present 190 are watching, sir.
Okay, okay, good.
One. Yeah, it became 201.
Okay,
Yeah.
good, no problem. Yeah.
Yes, sir. Yeah. Yes, sir. Yes, sir. Yeah. So, welcome back, participants. Now we are entering to the second session of the STTP, and we have the expert from IAC Bangalore here, Dr. on realistic experimental test beds, micro and smart energy systems, hybrid test bed. Hearty welcome, sir. It's my privilege and honor to introduce Dr. Gurunath Gurula, sir, Assistant Professor of Department of Electrical Engineering, IAC Bangalore, to this 1 week STTP. Just some delay is coming. Yeah, okay. Dr. Gurunath, sir, received his BTech degree from SVH College of Engineering, Nagarjuna University, Guntur in 2001. MTech from Jawaharlal Nehru Technological University, Anandapur, India in 2004. PhD in Electrical Engineering from Indian Institute of Science, Bangalore, India, 2010. And he is a postdoctoral fellow from Texas A&M University. Okay. Yeah. Sorry, sir. Actually, there was a echo was coming. Okay. And postdoctoral fellow from Oak Ridge National Lab, Tennis, USA. SIR International Travel Grant 2009 to attend IJCNN 2009. IEEE CES 2009 Student Travel Grant. He bagged the Best PhD Thesis Award in 2010 from Department of Electrical Engineering, IAC Bangalore. Best Conference Paper Award in IEEE PES General Meet 2015. Best Poster Award from IEEE Industry Application Society Annual Meet from Dallas, USA in 2015. He received Young Scientist Grant in 2015 from Department of Science and Technology. Young Engineer Award 2015 from Indian National Academy of Engineers. Second Best Poster Award from IEEE PES T&D Conference from USA. International Travel Support Science Engineering Research Board from SERB, for attending ISGT USA, and IEEE Power and Energy Society Outstanding Engineer Award in 2018 for the contributions made to IEEE PES Bangalore chapter activities. He's a senior member of IEEE, and he has several publications in reputed journals, which includes IEEE Transactions on Power System, in which he has n number of journals, IEEE Transactions on Smart Grids, IET Generation, Transmission and Distribution, Electric Power System Research, Sadhana, Indian Academy of Science, etc. Also, he has authored more than 30 international conference publications. Furthermore, adding to his profile, he has 3 granted patents in his account on systems and methods for predicting power system instability, systems and methods for controlling power system stabilization, and a filed patent also. His current research activities include high performance computing applications and power system analysis and control, nonlinear and intelligent control applications in power system, weak grid interconnections of renewable energy, microgrid protection and control, smart grid control and stability, renewable integration, etc. He is a renowned academician and researcher who has provided many significant contributions in the area of power system stability and grid integration and control of microgrids. Now I request Professor Dr. Gurunath sir to take over the session.
Thank you. Thank you very much, madam. Am I audible to everyone? Is
Yes,
my
sir.
voice clear?
Yes, sir.
Okay. So I might be having problems with the network because from the morning onwards it is slow. So I will switch off my video and then start the presentation. Is
Sure,
that fine?
sir. Yeah, sure, sir. No issue, sir. Yeah.
Thank you. Can you all see my screen?
Yes, sir.
Okay. Very good afternoon. I am Gurunath Gurala from Department of Electrical Engineering, Indian Institute of Science. This talk is basically, I'm going to discuss about 2 test beds that we have built in the last 4 years. One is a microgrid test bed and another one is a smart energy systems hybrid test bed, which is still under progress. So let me take you through what is our department. So Department of Electrical Engineering has been established in 1911 in IISc. IISc itself started in 1909. So our department is one of the oldest departments. We have about 25 faculty members who work in predominantly in 3 different areas: signal, image processing, and language processing. And we have faculty working in machine learning and computer vision. And we have faculty working in power systems, power electronics, and high voltage. We have about 25 faculty in total. And I work in power systems area. So I predominantly work in power systems stability and control, smart grids, more on sensing, analytics, and machine learning applications. I also work on high performance computing applications like GPUs and parallel computers for the large system analysis. I work on V-grid integration of renewables, microgrid modeling, control, and protection aspects. So let me give you a motivation why we wanted to build the test beds. First of all, if you see, most of the power engineering departments in the world are actually using a lot of simulations, so mostly computer-based analysis and simulations. Because of that, most of the research stays in the papers, and the technologies are only validated on the simulation. So this becomes a barrier for the industries to absorb such technologies, because they don't have confidence whether it really works in the field, because we are not doing any implementation as far as the work is concerned. So what we thought is that if we start doing experimental research, predominantly only power electronics community and some high voltage engineering people work on experimental, but most of the power engineering community works on simulation basis. So early days, like up to 80s and so, we have been working significantly on experimental research as well. But with the advent of these computers and simulation, most of the experimental works have actually gone. So we thought there is a need for experimental research so that students can make their hands dirty and understand the implementation aspects and take whatever they do as their parts of PhD and masters. When they go to the industry, they will be confident in taking those aspects into a product where there is a significant challenge in implementation. So we feel that definitely with experimental research, although you do it on a very small test bed, it gives a lot of confidence for the industries that this can be implemented. That is the first confidence. The second thing is you will definitely get well-trained workforce who are confident in doing things rather than using things. So because of that, they can get good products and technologies to the industry. So that's what is the goal of the test beds across the world. You can see that in the last 10 years, the research funding has been significantly increased in creating the test beds so that industries can actually get benefit out of it. So the background, basically, power grid technologies are mostly looking for situational awareness, cybersecurity, resiliency, renewable integration. These are the major things that are actually today a need of the hour. And industry needs technologies which can be turned into products. So industry doesn't want a paper if you give to them, and they don't want a paper. They want to say, okay, have you implemented this on something? So experimental research will enable such things so that industry can come forward and seamlessly integrate with the universities to do a lot of product development as well. And the challenge here is that power systems basically is a system. It's a vast. So representing them in a laboratory and making sure that it can scale and reconfigurable. These are the two challenges that needs to be addressed. It is very difficult to address all the things, but we are trying to make an attempt to do this. So first, I will explain about a microgrid testbed which we built through funding provided by National Perspective Plan for Research and Development by Ministry of Power. And it is actually through Central Power Research Institute. So the goal of this project is to build technologies for microgrid. So we have worked on power conversion, that is the development of power electronic converters. We worked on the control. We also worked on the protection technologies. So I will brief about this in a couple of slides. And then I will go to the next test bed, which is still work under progress. This work is just concluded. So it is started in 2017 and ended in 2019. Okay, so let me spend a little bit of time here. Sure whether I can put a pointer. Okay, so just see if a pointer can be enabled. Okay, I'm sorry. So on the left, what you are seeing is the layout that what we have envisioned to build, and what we have built exactly the same layout on the right side, the practical implementation. So what we did here in this test bed, we have actually made 2 feeders. And on each feeder, you can see that these are benches which are made available with all the MCCBs and all, so that students can create different types of sources. Like one source maybe with PV, one with capacitor banks, or one with storage, all the stuff. So you can see that this microgrid has an option to provide 1, 2, 3, 4, 5, 6 feeders, and 6 feeders with sources basically. So there are 6 feeding points to this microgrid. And then we also have points. You can see that these intermediate points, which the cursor is shown, these are the points where I can add impedances, or I can also add loads to that. Okay, so and this each feeder is independently fed through a transformer, so that I can actually isolate from the main grid. So the main grid is 11 kV supply to our lab. This is a high power lab in electrical engineering department. So there we have actually provided 3 different aspects, because this particular grid what we are having doesn't constitute any kind of particular characteristic of different grids. For example, you want to change the X/R ratio, you want to change the short circuit ratio of the system, then it is very difficult. So there, what we have provided a grid emulator, local grid emulator, which is developed by our own students, which essentially can mimic different grid structures at which this microgrid can customize. You buy uh, have the ability to customize so that you can actually use different kinds of rules and different kinds of excitation systems, and all that stuff can be done. We also have some single phase loads place for single phase loads. And you can see that each feeder can be independently closed and opened, and a complete system is actually communication assisted. So we also have communication system and a control and command center which is created. So now I will go to the right side of it, and you can see that the entire structure what we have is actually created as panel here, and all the wiring has been extended from here to the physical locations of the sources and the loads. Now the student, what the student has to do if he has to do an entire microgrid, so first thing he has to do is make sure that there is a graceful startup and a graceful shutdown that is actually feasible. Then to do that, he has to basically turn on he has to turn on all the MCCBs at the individual tables, and then he has to come back and program in this. You can see that this is the control and command center. In this, he can actually start turning on the main grid supply. This corner is the main grid supply, so that he can do grid connected as well as non off grid kind of a simulation. And every feeder, so here you can see 1 2 3 4 5 plus 10 here. So this is going to take it to 6 sources and 4 load points. So you can actually turn on these feeders in a nice way. And you can see here on the red side, the red colored boxes that you are seeing here, these are connectors, where if you want to add some impedance between two sources, like distribution system impedance, then you can actually connect any impedance between these two terminals from a point. And this is also having an MCCB protection, so that you first turn off and then connect it, and then you can turn on again. So all the industrial safety precautions have been taken care in designing the entire system. Okay, and it is already designed and commissioned. We have tested multiple sources, and everything is working fine in the lab. And anybody happens to come to Indian Institute of Science, you're all welcome to come and visit this facility. And this is one example of the source I am talking about. So this is a grid-tied battery inverter setup. And there are a couple of publications we have in this particular aspect. So I'm not going into the details of any of these things, because these are all research work that has been done by PhD students. So basically, we have option for connecting either a UPS, we can connect to a load, we can connect to a grid. So multiple options are available in these converters that have been developed by the students. And we also did ultra capacitor energy storage as one of the sources. You can see here, this is the stack completely developed in-house by the students, and this is the inverter cabinet that has been developed. Cabinet as well as the entire thing is actually being developed by the faculty and the students. And after we finalize the design and the complete layouts, then it has been manufactured, outsourced for manufacturing, but the complete thing is customized and designed by us. So, and the other one is the most important thing is connecting to the grid as well as disconnecting from the grid, detecting islanding. These are the most important things as far as the microgrid is concerned. So we have developed a custom uh, platform which actually allows you to seamlessly synchronize to the grid and disconnect from the grid without having any jumps in the responses of your system. So we have developed some controls for transitioning from islanded to grid as well as grid to island, and there are a lot of works that have been published in this particular area. So this is all about the microgrid testbed. So any further details you can need, please you can get in touch with me. If you can just type my name in Google, you will get department's website, and you can find out my email ID, and you can always contact me. So the second testbed which I'm going to describe is Smart Energy Systems Hybrid Testbed, which is about 6.5 crores received from FIST, which is a DST funding. And in this, we are actually in the second phase where we are developing the control center and the SCADA system behind that. So I'll go through this now. So basically, if you just look at why we are doing this, in power system R&D, you will be mostly working on either on system level algorithms, or some people might be working on field device algorithms. For example, you might be working on a novel distance protective relay, maybe a novel PMU algorithm or something like that. So the research is either on field devices or on system level algorithms. Or there may be something like transmission and generation controls. So some people work on FACS, HVDC, and then some people work on AGC and all these kinds of stuff. And with mix of renewable energy sources and hydrothermal and different kinds of loads and these kinds of stuff. Now, and there are actually research topics where people work on communication between different areas, how the algorithm should be protected, and the control center and the field, how the cyber security can be improved and all these things. So is there a possibility that we can develop a test bed, even though it is small enough, but it can actually show the proof of concept of what you have done in simulation, that it will work in field? Because this is very important, because the moment you want to implement something in the field, the timing of how the measurements are taken and what time it is received at your control center, and or how much time you are taking in your actual PMU device or embedded system to take care of all the issues that are involved in the entire loop, because you're talking about a system. So these things are the major challenges in implementation, which takes a long time for an industry to realize something which is in a paper to a product. And if the students are trained on how to do these things meticulously, then the time that students can take for productization can be significantly minimized, and industries get benefited by the PhDs that we are producing, or master students who are being coming out of the institutes. So one major challenge in system theory as well as the practical implementation is concerned, especially in power systems, is that in a practical system, you would always see that the system has what is called as a substation, and this substation is always treated in our research as a single line or a bus where multiple things will be connected. But if you see the significant research in smart grid and all happening in substation automation, different protocols like IC 61850, digital substation, digital twins, now, all these things has significant impact on how we will see our future power systems, But to realize that, we need people who understands the implementation strategies. For example, I'm sure that 70 to 80% of the PhD students who graduate out of even the premier institutes are not aware of how the substations are configured and what are the challenges in it. Okay, so to bridge that gap, we have actually developed a realistic substation environment so that people can actually implement their protection techniques or their system level algorithms, getting data from this. So what do I mean by substation configurations? For example, you can see it here. To just connect three particular lines, one transformer and two lines on the downside, the substation will have what is called as breaker and half scheme, which is widely used in all the 400 kV substations in India. And this is something called as ring bus scheme, which is also being used when high reliability is required, especially for giving power from different feeders to a city or that kind of stuff. And there are other configurations too, which I will explain in future in the next slides. And how do we realize this? And the protection for these is more challenging than if you just assume that there is a line and you're going to take few current and voltages and do it in your simulation. Let me tell you that if you want to actually do a protection for a line like this, you must be needing so many voltage and current inputs and status signals of these lines. And you also have to take care of the communication delays that are coming and whether your automation system is working or not. Whether if it's many people, I have seen that they're building some protective relays on some beagle bone and this kind of general purpose hardware systems. But do they meet actually the requirements of the timing as far as the substation is concerned? So these are all things that can be actually explored using a test bed like this. So we thought we will have a detailed substation, and then all the ingredients, field devices, we can have even a control center in the lab so that people will understand exactly how this is being implemented. For example, we know about state estimation very well, but I am sure that many of you don't know how it gets exactly implemented in the field. This is something which we wanted to get to the students. So the overall goal of this test bed is to have something like this, where we wanted to have an experimental power grid of maybe a small system, maybe up to 6 generators. And then remaining things, we wanted to do it in a real-time simulator. Although we have not yet started this part of the work, which is in the second phase we are starting, but this experimental power grid part we have succeeded to a large extent. And then we can have a physical protection and measurement systems here, and we can have the complete visualization and energy control center, all the energy control center features within the lab itself. Just like the way if you go to a SLDC, Southern Load Dispatch Center, or State Load Dispatch Center, the way you see the system working, we want to do the same thing in the lab. So we actually build the entire system from scratch. So we have not purchased anything so far which is off the shelf available. In fact, there's nothing off the shelf available the way we want to build. So I will go through what are all the things which you have built and our goals. So this is what is our lab in IISc. This has about 3 big rooms in the ground floor of electrical engineering department. So in this first room, which I'm showing here with the cursor, you can see that 1, 2, 3, 4, 5 physical machines. And at this place, you can see that these are loads, load banks, basically RLC loads. We also have power electronics based emulation so that you can do different loads. And the transmission lines and other stuff are actually in the second room, where we have basically you can think of this room as a generators like an NTPC or something. And this middle room is basically a substation. So we have 6 substations. You can see the 6 boxes here. These are 6 substations where students can actually interact the way they do interact in a field. And on this side of the room, we have a place where students can connect any network topology that they want to connect. Let's say we have 6 generators here, so 5 in this room and 1 in this room. So all these 6 generators can be made up to a 6 bus system, or more than that, depending on the number of transmission lines that we have. So we are actually planning 6 transmission lines to initially actually establish a 3-machine 9-bus system, which is widely used across all the disciplines in power engineering. So you want to actually establish a 3-machine system. And then this room, you can see that we have this one generator, and then this is what is called power amplifier. So we are building our own power amplifier. Everything in this actually built, customized within the country through the local industries. So I will show you what we have done. So power amplifier, one PhD student is working on developing a power amplifier which can actually withstand the short circuit currents through. And in this room is where we are actually trying to create a control center, just like the way you will see in SLDC, and the real-time simulator. And this server, what I'm showing is the energy management system, where the students are working on developing next generation energy management system architectures, so that you can handle renewables, you can handle battery, you can handle demand response, everything in a single umbrella, instead of having multiple systems talking to each other. So this is the overall plan of building. So far we have finished these first 2 rooms, transmission and generation, and the third room, this generator is also done. And we also have a battery backup, just like a substation will have a direct battery feed, so that even a small jerk in the voltage is actually avoided, to make the system perfect as far as the tripping and other signals are concerned. So same way we have implemented in the lab also. So we are under the process of doing this half portion, which is including the power amplifier portion in the coming years. So I'll show you these 2 rooms, what we have done so far. So let me take you to the generation room. So what we are trying to do here, we have built a custom generator. Of course, we have old generators called Maudslay machines, which actually have per unit on say 5 kVA or 3 kVA basis. If you look at their per unit values, they're exactly similar to a large generator of 250 MVA machine, except for the time constant of it. So similar machines we have, they are not available today to buy. So with a local machine manufacturer, IE Power Technologies, we have actually built this machine, which has a DC machine and also a synchronous machine. This is a 5 kVA. So you can see that at 20% rated voltage, if we do a short circuit, you can see I'm actually getting about 50 amps as the peak for the short circuit. This you will not observe on a normal machine, because it are not. So amps at 20% current in this. So this machine, like this, we have built about 4 machines, and all the 4 machines are actually installed in the system. Now we did a rigorous test on getting the parameters of this system, and we can see that this range of machines parameters versus what we achieved is more or less very close to the big machines, except for few things which we can actually do through other emulation. For example, time constant will never be same as what you will have, because these machines are at low voltage and high resistance. So you need to actually use some control mechanisms to actually implement these kind of time constant modifications. So this is how the machines are there. We also have a doubly fed induction machine. This is a regular normal doubly fed induction machine. We also have a permanent magnet synchronous machine. So we are working on controlling these machines to behave like a big 1.5 megawatt turbine, or a 2.5 megawatt turbine, or whatever that you want. And we have control panels for each of these prime mover machine as well as the main machine. So the prime mover is basically, in these two cases, it is a induction machine, whereas for the synchronous machine is the DC machine. So we have control panels like this. Now what these control panels have, it has all the power electronic bricks that you need to control your machines, but none of the controls are actually being developed. So the goal is that the students would be able to develop by themselves the controls required so that it can behave like a wind turbine. So instead of just using a Simulink to do the controls, you will be actually implementing the controls and understand whether the performance what he designed in simulation is able to achieve in a practical way or not. So that's the goal of these controls, and none of them is programmed, so students have to program them to actually make a system running completely. So we already did a few the synchronous machine emulation completely. We are still working on the wind turbine emulations. So this is the lab. If you come to the department, you will see lab like this with all the controls on this side. I want you to focus on this small box here. So this small box has actually a connector that you can actually connect. So these boxes are basically the output of each of these machines. Like synchronous machine have 3-phase output, and we just connect to this box. And like this, from every source, we will be getting this complete power supply at one location, so that you can make actually whatever topology that you want. Let's say you want to configure a 3-machine system, you can do it. I'll show you that particular thing later. So this is about the lab that we have right now, and students are working in this. I'll show you some results that we have. So one of the student has actually developed the IEEE 421.5 compliant static excitation system using buck boost converters, and these are some representative results. You can see here, these are the generic converters that we have. The same converters are being used in the panel, and this is the machine that I told you, it's a old machine. And now we have dumped all the development that we have done on this old machine to the new machines that we have developed. And that exercise is going on with one of the PhD students. So we have implemented exactly the way the excitation system actually interacts, where you have to initially field flash and then start the excitation system. Then you have to gradually turn it onto the terminals. So automatically the exciter gets power from its own terminal. So this is how the entire system is created. And we also did a thermal turbine and governor emulations. We have taken different kinds of governors, and these governor models have to be reproduced. For example, if I command a torque for the machine, it has to be exactly like the output of a thermal turbine. Then that has to be emulated by the DC machine. So the student has actually developed the controls so that he can emulate mechanical, electrohydraulic, digital governor, whatever you want. It has to be emulated by the student so that he can actually mimic a particular generating station. So what is the goal? For example, let's say some RTPS or any power generating plant guy has some issues with their governor, or they wanted to get some models to be developed by a university. What they have is only measurements, but they don't have anything to do. So what we can do is actually get those measurements and take those measurements played on this particular set, and then we can tune the controls and say, hey, these are the controls that you can actually use so that your governor will perform well. So similarly, you can do PSS tuning and all that stuff, experimentally validate, so that the person who's actually receiving guidelines from you is more confident that, yes, this will work in the field too. So this is something is the goal. So let's see how we'll progress towards. So this is one setup we have, which is basically a single machine infinite bus system we created just to test how all the controls are working. They're working fine. We could see about 1 Hertz frequency oscillation in this. This is the Pi network we have, but we also have different kinds of transmission lines we have emulated. I'll show you what kind of transmission lines we have emulated. Okay, so the next thing we actually wanted to do on this system is to create a reconfigurable source emulation platform. So for that, this is the kind of experimental setup. So the controls which I have is this. Basically what it means, I have a front-end converter which will be interfaced if required to any machine that you have, like it can be a synchronous machine or DFIZ or a PMSM. And we have a DC machine for which the power will get from the grid, and then all the controls that you wanted to emulate needs to be coded on this. So what is the goal? Let's say you want to emulate a hydro turbine. Yes, you should be able to emulate a hydro turbine. If you want a different excitation system, for example, ABB excitation system, ABB gives you just one block diagram and doesn't give anything. Even he will not even give you the parameters what you need. So maybe you can actually take that block diagram and you can code onto your system and then actually emulate your machine behavior on the synchronous machine, and then try to tune the parameters so that you can actually take a coordinated tuning effort of different controls in your power grid. So that is something you can actually do in the generating stations. You can have different PSS can be done. And the most important goal that we wanted to achieve is, let somebody says that I have only a 50 megawatt turbine, and I have some measurements, maybe from a fault recorder or from maybe from relay records or something like that, or PME records. But he says, hey, I need a model for that. Can you give me a realistic model? This is actually a big research challenge. And there are a lot of things people are doing using what is called as the software packages. But what we wanted to do is that we wanted to actually expand that scope to a real scope where not only getting the model, but also you can keep on continuously check whether the controls are actually good enough for this kind of a system, whether the controls are tuned very well. So we are going to the next step where you can validate the controls and all that kind of stuff. So this is something like a hardware test bed that we are building for source emulation. So this is our first goal, and we are halfway through, and we are still, of course, this is a long way. This whole research will be keep on going, and multiple PhDs will come out of this kind of a work. Okay, so the next thing that I like to explain is transmission. Am I audible, and is there any disturbance in this so far? Okay. Madam, Asha madam? Hello?
Yes, sir. Yes, sir. Hello, sir.
Is everything okay till now?
Yes, sir. Everything is fine.
Okay. Yes. Thank you. So I'm going to the transmission section.
Yeah, please, sir.
So here I will take you through a different understanding of what a substation is, and we have created a substation just like it appears in the field, substation control panels. So let me show you what are the different configurations in substations. Predominantly, there are 6 kinds of substation configurations that you use. What is called a single bus, single breaker. That means there will be one live bus where the incoming will come, and then it will go to the load. There will be only one breaker to protect the load. There is what is called as double bus with a tie breaker. So basically, there will be 2 energized buses, and the 2 energized buses will have a breaker. And whenever you want to transfer from one bus to other because of the fault, you can actually do that. And this automatic transition, or you can actually do manually, is something which is very important. And when both the buses are energized, then you will be having protection needs to be shifted from one bus to the other bus. So there are some logics that needs to be developed. And then you have main and transfer bus, which is also having 2 buses, but there is a slight difference between double bus versus main and transfer. In a transfer bus, it can take only one feeder at a time. It cannot take all the feeders. whereas in a double bus, both the buses have the same capability. And then you have what is called as breaker and half scheme, where for every feeder that you have, there are two breakers which will need to be controlled to isolate this energized device. Essentially, there are two buses which are actually active or energized in this scheme. There is something called as double bus double breakers. So predominantly in the country, what we see on all generating stations, you would be seeing either main and transfer bus or double main transfer bus. So these are the two you will see. In distribution systems and breaker is predominantly used in very high voltage substations like 765 and 1200, where you need extreme reliability. Here you will have, for one feeder, you will have two breakers, dedicated breakers, and there will be actually two buses which will be supplying or energized at any point. Ring bus is a configuration which is used when high reliability is needed and multiple feeding points are there. Ring bus is being used. You can actually see a very nice block spot by a practicing engineer called Gopalakrishna Palepu. You might have heard him. He's actually giving trainings to a lot of young engineers who join AP Transco or Telangana Transco, wherever. So he has very good lectures on how the practical protection system actually works. You can see there are a lot of textbooks too, which explains all these configurations. So our goal is, at any point, if you go to a substation, there will be only one configuration. Like this particular, let's say double bus, you say, it will be a double bus double breaker. But as a researcher, you should know how to protect all these systems. At least you should be experienced, or you wanted to do some schemes which specific about like breaker failure schemes that you want to test. Then you need this configuration to be implemented. If you do it in simulation, then you will only get whatever you simulate, but you don't see the practical aspects of whether the data is communicated, is it communicated in the right time, whether the signal is received at the right point, how much variation I can still allow so that the protection system works with utmost reliability. These are all the practical concerns that an engineer has to take care. So in order for the students to get this particular aspect, we built a generalized substation. So basically, we initially built a scheme where we can try to realize all configurations in a single substation. I don't want to go through this particular diagram, but I will show you in a nice way. So what we have done is basically we wanted to implement a substation. So we need breakers, and each breaker will have two isolators on both sides for manual reopening. And then we also have what is called as earth switch to the system. So you cannot actually you have to have an earth switch so that you can actually completely isolate the person. Before the switch is closed, you cannot, even any person cannot go and touch the systems. So all these things have to be taken care, and there is a significant logics that you need to build so that all these work in a proper way, the way it works in the field. Another point that needs to be looked at is any breaker that works, basically it has to work within the maybe 2-3 cycles. All right, so then you need to actually choose something which works as a breaker. So we have to actually look at contactors which can actually give timings that are in the same as a real breaker. So we looked at different ABB contactors, 3-phase contactors. We looked at Schneider and Siemens 3-phase contactors, different varieties, and then finally narrowed down to this 116 amps ABB contactor, which has a closing and opening times well within 3 cycles of operation of our system. So this is something we have used. And another thing that we have used is basically, if you look at the operation of the substations below 132 kV, most of the time they are gang-operated circuit breakers. That means all 3 poles or all 3 phases will be opened simultaneously or closed. You don't have what is called as independent operation of the phases. Whereas if you go above to 132 kV, most of the high voltage substations have independent pole operations where you will do auto reclosing if there is a short fault, I mean short duration fault, and you will auto reclose and then that particular phase and then automatically recover the system. If it doesn't work, then you will completely trip the system. So in order to enable that kind of a stuff, we have used two contactors, three single phase contactors as well as one three phase contactor, so that you can achieve both the operations in the system. So this is also has a very small, the last one is the single phase contactor, which has a very small operating time, so that you can actually mimic a circuit breaker operation reliably. It's not exactly reproducing any of the transient behavior of circuit breakers, but for power systems analysis, it is enough if the circuit breaker can actually show me act as a switch. So I think this is actually more than enough for me, for our kind of applications. So that's what we have done, and this is what the lab looks like today. It is already installed. If you would have gone to any substation, you might have seen this kind of what is called as mimic diagrams, which actually tells you how to operate your system and the complete connectivity of your substation. So you will have panels where you can actually turn on a breaker, turn off a breaker, turn on an isolator, turn off an isolator, and then you will have annunciators which will tell you some status signals of different things. You will have meters and all that stuff. So we have actually 6 such substations built. These are all completely custom built by us. The complete planning and everything, component selections and drawings, everything is being done, and then it is manufactured through a company called Adobe, who have actually requested us to actually commercialize these substations. Not only the substations, also the generators by IEPT, so that many of the universities can be benefited with this kind of developments, and they can actually give practical knowledge to students. What is the benefit of this particular substation? I will tell you that everything that what you do in a practical substation is available here. So I will explain a lot of those things now. So this right hand side, the panel that I have on the right hand side, what I have, I told you guys to actually focus on a small box. So this box is where I can connect the output of the generators. Now all these boxes outputs are taken and they actually terminated on this particular panel on the right hand side. Now in this panel, what you can see on the left corner, this is the sources, and then what we have is substations, and then what you have is actually transmission lines, and then on the last panel you have load points. Now if I want to connect sources to the loads, it is not a bus. It is now has to go through a substation, just like in the field it has to go through. So person has to make a connection from here to here, and then from substation to the load. It's just like a practical connection that you will be making. And then I will explain you that each substation, how it is and all that stuff in the next slides. Okay, so it's a very important point. This is actually taken from this blog spot, Gopalakrishna Palapu's blog spot. You can see that if you have a breaker and half scheme, in actual practice, the number of CTs that you will be using to actually do a particular protection is varying depending on the substation and depending on the company which has actually installed that particular protection system. For example, there can be what is called as 3 CTs. What it means, there is a CB and both sides, the blue dots are actually the isolators, and one side you have a CT. And again, this side, one side is the CT. Whereas for this, you have a CT on this side. Now, the arrangement can be, you can have 2 CTs in the middle, and you can have 1, 2, 3 CTs and 1 CTs in the feeder, which is actually going. Again, you can see. So there are like 5 CT, 6 CT, 6 CT. Again, there is a variation, different variations, and 8 CT. So depending on the substation, you have a different actually opportunities to do. Now, are we aware of all these things? but a practical engineer has to handle. If something happens, what happens is they have to call the person who has installed the scheme and then check is the problem. Instead, if we are all trained well and understand the schemes very well, then we ourselves can actually gain that knowledge and actually reduce our downtime when something happens. So this knowledge is very, very important. So what we did is, in this substation, what we created, we looked at all the configurations, and then what are the maximum number of CTs that you need, or CT connections that you need, we have looked at. And then we said, okay, we will remove what is called as backup protection, everything, because for lab substation, you don't need backup, just main is enough. So we removed all these, the terminology called as main 1 and main 2. So we removed the main 2 requirements, only main 1 we considered, and looked at how many CBs are needed, and all these CBs are actually kept inside the substation. And we used metering CTs of 0.2 class accuracy and protection CTs of PS class accuracy, so that you can actually do protection and metering in different ways. Okay, so this is how my substation actually looks like. So I don't know how many of you actually understand the single line diagram of a substation. So for example, you have like bus 1, as I said, bus 2, and then transfer bus. So there are 3 buses basically, which are nothing but copper bus bars, or maybe aluminum bus bars. You might be seeing that in the field. And then each can feed a different feeder. So in this substation, we have total 4 feeders. I will show you the complete diagram. But you can see that in the middle, the number 52 is actually indicates the circuit breaker, and 89 indicates the isolators, and CTs are also actually numbered here. And you can see A at the end, E means earth switch. Although we have not physically implemented earth switches, we have created electronic switches, and their interlocks are actually made available so that you can actually create the earth switch emulation in this particular thing. So if you see here, for the breaker 1, I have 3 CTs on the top and 5 CTs on the bottom. You'll be surprised why you are saying there it's only 1 CT or 2 CT or 3 CT. But here there are 5 CTs on one side and 3 CTs on this side. When I say in the previous diagram there is only 1 CT or 3 CTs, each CT will have different secondaries, maybe 1 for metering and 2 for protection, depending on the scheme that you have. So to realize, it is not a single CT essentially, it is actually 3 different secondaries also has to be there. But making a CT which has 1 primary and multiple secondaries requires significant money. So what we did is we used single primary CTs, so that single primary and a single secondary CTs of 5 numbers, so that I can create just like a 5-core CT. So this can be treated as a 5-core CT, and this can be treated as a 3-core CT on one side. And you can also see this is the feeder, 1 feeder, and also has a feeder CTs, which are again treated as a 5-core CT. And we also have a potential transformer, which is both metering and protection class, and with two secondaries. Again, we have for each bus, you have the protection, PTs. And this is how a real substation you will be implementing. It's not a single CT or a single PT. There will be multiple PTs and multiple CTs that will be coming. That is why a protection in the field is actually challenging. Okay, so this is how my substation single line diagram looks like. So you can see that I have 4 feeders, feeder 1, feeder 2, feeder 3, feeder 4. And I can realize the way we have set is we will have different knobs on the substation. So one knob actually tells me that, okay, can I gives you option of one particular configuration, let's say breaker and half. The moment you select it, it will actually allow you to work only in breaker and half configuration mode. So what it means is breaker and half means there will be 2 buses. For example, I will show you one particular thing. Let's take a case of single bus single breaker. So if I select option 1 in that switch on the substation panel, then it will be set to single bus single breaker. What it means is that although I have so many breakers, see, this is one breaker, this is one isolator, there are so many switches are there, I cannot turn on and turn off any of those things. I can only turn on and turn off the ones which are highlighted in this route. I can only turn on and turn off only these. That means I can only on this breaker and this isolator by myself, and others are, even if you turn on and turn off, they will not even operate. So that's how we have to actually do a programming and stop operation of these switches. So which is a big programming one master student has actually done. It's a 250 pages of PLC code that has been developed for this particular substation. So this is how I can do a single bus single CB. That means only one bus is always energized and all feeders can be actually done. The second one, let's say it's double bus tie CB. What it means? So I have this bus is completely on, and the second bus is also completely on. And between these two, I have another CB which is completely on. So now you can turn off this CB or turn on this CB and these isolators, and only these can be actually done. If you want to actually shift one feeder to the other feeder, let's say there is some maintenance work needs to be done on for this bus, then you can actually shift it. So how you need to shift? You can shift like this. So that means the complete control will goes to that. Now, how do you implement this? This is something very important. You need to create that scheme inside your bus control unit, and that is something which is a practical knowledge you will gain out of this kind of work. So there is another configuration that you can do, what is called as single bus transfer. So single bus is one and transfer bus is the bottom. So you can see that only corresponding breaker which connects between bus 1 and transfer bus is enabled now. And anything else you want to turn on also, it will not be turned on. And one important thing that you need to take care is that you can only transfer only one at a time to the transfer bus. So that means you can only transfer like this, one feeder to the other. Once you transfer this to one feeder to the other bus, then even if you try to transfer the other feeders to the transfer bus, it should not allow. So this is something called as interlocks mechanism that you need to actually code into your bus control unit. And this is a practical aspect which you will be learning out of this kind of systems. So either, I mean, I'm just showing all. So these kind of things can be done. Similarly, the same substation, you can actually do double bus transfer. Very simple. Either you can transfer to double bus or you can transfer to a transfer bus. So that means in that case, you will have both these feeders will be enabled. And all these things have been taken care in the system so that there is no problem for the students to actually realize these things. Similarly, this is what is called as the breaker and half scheme. So where you can see that these two are disabled now, and this one, bus 1 and bus 2 will become your main buses. And you can see that 3 breakers are there. For every feeder, you can see there are 2 breakers that needs to be controlled. So now you can actually realize a real protection, just like your field, you can do a protection here. Similarly, you can do double bus. In the double bus scheme, you can only use 2 feeders, so you cannot use all 4. So these 2 feeders will be energized, and you can do a double bus scheme. You can see that this feeder is this breaker will never be able to on or off in the double bus scheme, so that only this breaker and this breaker will be on for the double bus scheme. Likewise, you can do a ring bus. You can see this is a ring bus configuration which you can do. If you select the option number 6, this gives you the ring bus. That means all the other things which are not highlighted, you cannot turn on or turn off. So basically in ring bus, I have one feeder here, one feeder here. You can see between 2 feeders, you will have a breaker. So this breaker and this breaker. Similarly for this, you have this breaker and this breaker. And this goes through this particular bus. Again, this breaker is completely blocked. so that for this particular feeder you have this breaker as well as this breaker, which needs to be done. This is almost like a double breaker scheme. Here 2 breakers will be there, but you will be always sharing with that breaker with other feeder too. So this protection, again, if you want to implement realistically and you want to check what is that you can do, let's say you want to use some other communication technologies and other kind of different boards, embedded boards, whether they meet this kind of requirements. I think all these things can be now experimentally verified, and definitely the industry will have very good confidence on what you are going to build. Okay, so this is how the panel looks like, as I said. So I will show you from the top to bottom, from bottom to the top, how the panel looks like. At the bottom, you have these. This is what the buses. I would say the bus 1, bus 2, bus 3, and then you have your isolator. This is the isolator. Then you have the CTs. In order to minimize the cost, we only populated minimum number of cores that are needed. So here you can see that in this table, the last point you can see, and whatever number of cores that are required, that much we have actually populated. And then you have you can see the breakers here. So this is one breaker, this is 3-phase breaker, and this is single phase breaker. So both you can actually use. So there is a switch which you have to select whether 3-phase operation or single phase operation. Then it will do actually bring wires to the topology panel. So the topology panel which I have shown, there you will have the connections. So now the student who is actually want to use the substation, he has to go there, connect everything, and then just like a real field, how you have to start black start operation. We only heard about black start operation. There are so many PhD theses produced on black start and issues and all that stuff, but there is no experimental way of doing such a black start kind of thing in the lab. And this is going to allow you, this particular platform is going to allow you to do everything that you do in the field, just like the way you do in any big substation. So we also have taken care of PGCIL, Power Grid Corporation of India, interlock mechanisms. The interlock mechanisms are very, very important for safety of the personnel. For example, if you wanted to actually take a circuit breaker off, okay, you take off, then make sure that load has completely thrown off, and then you turn off your you have to turn on your earth switches, and then open your isolators. So there are a lot of mechanisms that you need to actually take care. These are called interlocks. If a circuit breaker is closed, you cannot open your isolators, because circuit breaker closed means it is charged and there is some load possibility is there. So isolators can never be opened without switching off the circuit breaker. Even if somebody wants to go and turn on also, it should not turn on. That is something as a very important logic, and we have implemented that so that people are familiar with the field practices of how things have to be done. Similarly, the earth switch operations all are taken care. Of course, control philosophies, a single pole operation, gang operation, you choose, make sure that all that stuff is feasible. And this is the topology connection panel. So a little bit of bigger diagram I'm just showing you here. So on the left-hand side, I have all the sources. So here I have provided for every source, I have 2 switches. Now, one switch is for connecting to the other side, and one switch is for, we have created a fault creation block, where we have used a power electronics to actually create a short circuit between A to B or B to C or any fault, and that will be that can be connected just here, so that you can create a bus fault. Now, if you want a branch fault, then you need to go to the transmission line and then create the same branch fault there. So that is the reason we have 2 things here. Now, for every source, so here we have like 6 plus 4, 10 sources you can use. 6 sources are physical, and then the remaining 4 sources can be like emulated from maybe either a power electronics system or from a real-time simulator through a power electronics interface. In the middle, what you have, is this particular substations. You can see each substation has 4 feeders. So each feeder connection is here. Now we can connect, let's say I want to connect to feeder 1 of substation. Then source 1 can be connected to feeder 1 and anything. So basically, a real substation can be as it is realized here. And here I have, you can see here, this is transmission lines. So I will show you what transmission lines we are doing. So from side and two sides, there are two terminals for any transmission line, from side and two side. So like that, 1, 2, 3, 4, and then here 8 plus 3, 11 transmission lines I can actually realize here. So we are only having 6 physical transmission lines, and then we will be having remaining lines be emulated in a maybe in a real-time simulator, and then they can be interfaced through a power amplifier to actually realize a transmission line. On the right, what you have is the loads, and again, as I said, each load will have 2 points, one for connecting to other system, the other for basically just for doing a short circuit at the load point. So like that we have developed, and remember, every safety precaution is there. So at the small box I have shown at the source, there is a MCB, student has to turn on there, then a light will on here, showing that, okay, something is already turned on. Then here there is another MCB which he has to turn on so that the power will come to this particular box, what I'm showing here. So this is how we will be doing the topology panel. Okay, so we have done some transmission lines, passive transmission lines. For example, this is transmission line which is being emulated using different frequency dependent model. We wanted to actually emulate up to 5 kilohertz frequency range. So we used what is called as model domain form, where you will use a Clark's transform. It is actually implemented with transformers. And then in the middle, you have RLC circuit. And this RLC circuit is actually fitted to frequency dependency of the transmission line. And this is the inverse Clark's transform. And we actually did an experimental verification. And we found that the results are very close to what you see in an EMTP RV. Of course, when we tested rigorously, you will clearly see that the damping in this implementation is much higher compared to the normal, because you have more resistance at 230 volts level. So we have implemented this kind of a line. We are now getting more such things. So we have actually simulated a 3-machine system just like this, and we tried to make sure that when you take a 3-machine system is a 220 kV transmission system, but you want to emulate it 220 volts. So make sure that the lines are emulated or scaled properly so that you have very less error in the physical system. So we did a power flow, actual power flow, and the power flow that you get in the 3-machine system that is there at 220 volts, and we found that the errors are very less. We are still minimizing the errors to less than 1% or 2%, but it is very hard to achieve this kind of a scaling. But we are largely successful in doing this kind of scaling. And we also did a transmission line emulation using power electronic converters. We built a silicon carbide based power electronic converter, back-to-back converter, which can actually emulate faults. So I'll show you, this is the setup, and we are able to emulate TSCAD results were able to track using this power converter. And there are a couple of papers published on this work. And these are some other results of transmission line emulation that we have done. Okay, so this is also another result comparison with the PSCAD versus actual results. And this is the stack diagram, which is showing the reproduced results from the PSCAD and the actual system. Okay, so we also did load emulation using power electronic converters. So we did JIP load. We also did different types of loads emulation, like constant current power with different percentages, induction load, induction machine load, heating loads, and all that kind of stuff. The goal is to use a power converter which actually emulates like a load and then feeds the power back to the grid, so that we are not really consuming any power in the load. So that is the goal of this. So we tried something emulation using power electronic converters as well. So the goal is essentially to build a 3-machine system. So each of this particular bus, what you're seeing, can be configured with any substation that you want. So that's what is the goal of this particular project. And we are yet to test the complete 3-machine system. We got the second phase funding where we have to buy the transmission lines. I mean, we have to manufacture the transmission lines what we have already built in numbers, so that we can actually establish this whole stuff. And the last one, which is the work is just started. So we wanted to actually build a control center. So the goal is basically we are using an indigenous real-time simulator developed by CDAC Trivandrum, IIT Mumbai, and ISC Bangalore together long back in NAMPAT scheme. We are trying to use this because the cost we ask for the real-time simulator is not being given by FIST. So we have to reduce the cost. Then the only way is to actually go with this. These are very cheap, and there is significant coding effort that needs to be done by the students, of course, but they will become learners, and eventually maybe one of the students may actually get very good ideas to actually build a real-time system, and he may start up a company. So having this kind of exercise are very, very important. So we are actually trying to use this kind of indigenous developed real-time simulators. We are also using a power amplifier built by our own students, so that they can actually we can connect a real-time simulator to the physical power grid, so that I can expand the 6-machine system with 6 transmission lines to a very large system. Let's say I wanted to do a IEEE 39 bus system, then out of that 6 generators can be outside, couple of transmission lines can be physical, and then the remaining can be in the real-time simulator. So this is something we are actually trying to achieve. This, believe me, that it's going to be a very hard task, and many research students are working. And if we are successful, this will be one of the best test beds in the world, I would say. Okay, so I have a video. Asha madam, do you have a little bit of time?
Sure, sir. Sure. Yes, sir.
Can you tell me whether the video plays or not, and you are able to hear?
Analyze the substation panel. It can work in substation configuration.
Okay.
This is the major controller in this. It's a programmable.
Okay, then let me start this video from first.
Yes, sir. Yeah.
Okay. The student you are seeing there in this video clip is my master student, and he finished masters, and then he joined with me as a PhD student again. So he is the person responsible for actually building the entire 246 pages of the code that goes into a Schneider PLC to realize all these configurations.
This is generalized substation panel. It can work in 6 substation configurations. This is the major controller in this. It's a programmable Schneider Electric programmable logic controller. So first I am going to select the substation configuration. Here first I am going to show the break and off substation configuration operation. So this is the substation selector switch. I am going to select it to operate in break and off scheme. So now this is in position 5. This is corresponding to break and off scheme. So now I am going to make it into break and off scheme. So I am turning on all the accelerators which is coming to this break and off configuration. So this one will come, this one will come, and this one will be coming, this one will come, this one will come, this one will come, and this will come, and this will come. It is connected to the second bus. So this is here, and this is connected to first bus. So this is operating in break and off now. Now for this side, see, I will turn on this, This will not run. It is connected to this, so this only will go. So it is operating in break current off. So now I will switch on all the circuit breakers to operate it in break current off. So this feeder is energized now. So this feeder is supplied through this circuit breaker and this circuit breaker. And this feeder, similarly, this also supplied through this circuit breaker and this circuit breaker. So now in this, now I will show the interlock operation. See, once the circuit breaker is on, these isolators will not be able to operate. Okay, so I am not able to off it. Or similarly, this also, if this is on, this I will not be able to operate. Off. Okay, this also I will not be able to off. Now come here. In this, I will switch off this circuit breaker so that it can operate. Okay, so now it is off. Now it can operate. See. And will be operated because the circuit breaker is off. Yeah. Now this can be on. Now this earth switch will not be able to operate because these two are already on. See. Now once these two isolators are off, this can be turned on. So I will show that first off. Now this can be turned on. I will off. Now if this isolator is on, also this will not be able to turn on. Now it will off. This is interlocked with these two isolators. Okay. Now similarly, for this isolator, these two circuit breaker must be off. See, now these two are on, will not operate. Now both circuit breaker are off. Now this can be operated. That is this circuit breaker, this line isolator is interlocked with this circuit breaker and this circuit breaker. Now if I close these two, these two are closed. Now I will not be able to operate. So if you put it into breaker adapter, the isolator related to transfer bus or double bus will not be operating. So I will show that these isolator which is not operating, I will operate and show. I will show that it will not operate. So look this. See, this one is not operating because it is selected to breaker and off, and this is also not operating. This comes to double bus scheme. So similarly, this also will not operate, and this bus coupler also will not operate. This operation will come only in double bus, double breaker, or double main transfer bus scheme. So these things will not be operating. And also in this side also, this one. So this portion will not be operated. Okay. So this transfer bus coupler also will not be operated. But these, whatever coming in this configuration will operate.
Yeah. So basically that's the video which actually tells you the complete operation of the entire substation. And so now our goal is actually to build one reasonable generating station physically in the experimental grid, and then the remaining grid in the real-time simulator. And then we wanted to have the complete physical protections. And then we also want to build the control center with a lot of new technologies that are there in database management, cloud computing, and all that kind of stuff. So this is something is our bigger goal. Hopefully we will be able to achieve what we envision in the coming years. So I want to acknowledge the DST, Department of Science and Technology, for providing the funding, as well as the Ministry of Power for the microgrid funding, and of course all the faculty members in the electrical engineering and the students who have been behind these developments, working day and nights to coordinate with the vendors so that they deliver as per our requirements, because everything is designed by us. So thank you very much. So with this, I will stop, and the floor is open for questions. Thank you.
Thank you so much, sir, for the excellent and very informative session. And participants have posted few queries. Like, I'll post that queries in the text box, sir.
Okay. Okay, so person is asking one question: how long a microgrid can provide power? Are you an electrical engineer, first of all? So if you are electrical engineer, then you should know that the dependency on providing how long depends on the availability of your source. If you are talking about a diesel generator, as long as you have your fuel, it will give you that much. And if you have say battery, as long as charge is there, battery will provide. And if you have a fossil fuel or gas based, or maybe any other renewable sources, then as long as fuel is there, you will get the power. So if you want to extend the time it will going to provide the power, you have to actually mix and match and try to have some additional sources. The second question: is it possible to configure grid through AI? I don't know what you mean by AI. So first thing is, AI has so many components. What do you mean by configure? So configure through AI means what? AI is basically is not today used as a mainstream direct controllable systems, or direct controllable systems. So it is only an assistive feature. If in future, if you have systems which are perfected for a given configuration, they may be useful. But I don't know what do you mean by AI that can be used. AI has many things. For example, you have today already expert systems are used for certain decisions. So that is basically already available. So you can have a look at it. Expert systems based decision making systems in control centers are being already used. But there is a human in loop always. Do microgrids increase the reliability of the grid? Okay, so see, the moment you increase the number of components in any system, the reliability will reduce. I think this is a common fact. When you talk about reliability, it has to be evaluated from different phases, not from a single phase. So there is no unique answer for that. The fifth question: what is the difference in stability of microgrid as compared to ordinary grid system? That is an interesting question. So in a regular system, if you see that the predominant electrical characteristics of a regular grid is completely different from a microgrid. A microgrid, the R by X ratios are very high compared to the R by X ratios in a regular grid. And in a regular grid, the distances are very high, so the impact transmission from one location to the other locations will have certain time, whereas in a microgrid, the impact transmission can be very fast. So there are many things that needs to be looked at, but at the end of the day, when you talk about the stability of the system, the tools that you use for the large system can be directly used even at the lower system with small changes in the algorithm so that they converge very well. So that I can say about it. Okay, so the next question is: can you enlighten on DC and AC microgrids application in a country like India, where already the transmission and distribution grid are well established? Okay, nice thing. So I don't know what we talk about the implementation of AC and microgrids at the system level. We already have a lot of microgrids in the system without knowing, because there are so many captive power plants being used by local industries who are reasonable sized, and we already use UPS in many of the places regularly. So microgrids, yes, they have potential, but how big way they can actually do is something depends on the policies of the system. In my take is, first we need to strengthen the distribution system what we already have, strengthen it and make the laws so stringent that everybody obeys the laws of the grid, and punishments have to be created so that people who obey will never redo the same, people who don't obey never redo the same mistakes to destabilize the grids. And if once you do that, then you can actually invite investments in for the remaining things. So there is a lot to do on the distribution itself before going to the next levels. At least the research can continue in these directions, but taking any steps to mass scale actually doing microgrids integration into the distribution grids is going to be like, you have a engine which is Maruti, but you have an outer case which is like a BMW. So you're only showcasing. Hope you understand what I am trying to say. Right. So the other question is, what is the status of the ultra high voltage lines greater than 765 kV? I think India is the first country to actually start very high voltages testing. For example, 1200 kV testing we have done, and almost all of the lines that are recently built are actually built for 765 kV, but we are operating at 400 kV. So we are already ready with those technologies as far as transmission is concerned. In fact, we should be proud that our Indian transmission grid is more advanced than many of the advanced countries, except for the control center algorithm utilization part of it. Our infrastructure is very robust. Can we use subgrids of different frequency like 50 Hz, 60 Hz on same hybrid microgrid setup? See, these are all things that you can always do as a researcher, but you should ask the question, why do you need to do it? It's your own unnecessarily complicating things, which is not required. Any solution that you want to provide tomorrow as a research has to be simple, and it should be implementable, and it should reach the people. So better you don't think something which is only just useful for the sake of papers. The other question is, what is the reason behind the short circuit happened recently in Hydel power plant Srisalem? Okay, I really don't have the knowledge. I'm trying to actually check for that, but I didn't receive any report so far, so I cannot comment on that. But definitely, this is something that we need to learn, that there is a short circuit happened and something very drastic happened, but still we are not able to do it. So one thing that is, we see, a short circuit to such a level cannot happen instantaneously. It must be happening from maybe a couple of days. So we have not used our condition monitoring advances that we have in the field. We have like thousands of millions of papers on condition monitoring, but we have not used them, because we say that we will have to do some investment and all that stuff. Maybe why not these kind of low-cost condition monitoring tools can be built by the universities and can be tested as just monitoring purpose. You're not going to control, right? So then we'll have a lot of indigenous technology there. Okay, considering the testbed on a maintenance perspective and complex fault has occurred, is there any provision to identify what was going wrong? That's exactly what is the goal. I want all my students to be very, very, very proactive in building the test bed. So now it is like you are building a new power system, and you know a lot of technologies, and I want the students to apply those technologies and show to the world that this is actually indeed works. So this test bed has provision for everything and anything that you want to work, right from artificial intelligence to anything in this world. So I mean, the sky is the limit for the research students who want to really do good research in power engineering. Question number 12, except Simulink, which other kind of simulation softwares are used to develop such kinds of GIDs? Frankly speaking, none of my students use Simulink. Simulink they will use only for initial prototyping or something, but everybody use their own code, either written in C language. Predominantly, many people write in C, C++, and then they actually use either Python or MATLAB coding. So I don't recommend students to actually use softwares to build stuff, especially masters and PhD students, because we want the students to be doers and developers, not the users of the advanced softwares. Believe me, all these softwares are actually built by a student like you and me who have gone to the MATLAB or somewhere and built it. So there is absolutely no need for a research student to actually simply start using them before learning how to build such tools. So first, to use something, you learn how to build it. That's the best strategy I would actually propose. Question number 13, is it possible to integrate grid with the distributed resources in Indian grid system in recent time? Yes, I think we have been doing that. So there is absolutely no problem at all. Item number 15, is it possible to have a capacity proportionality in a microgrid? I mean, definite proportion of wind, solar that give a better stability in grid-tied system also can we decide this distribution? The question is, theoretically, yes, it is possible, but many times establishment of a microgrid actually has so many environmental as well as the physical factors. Let's say you wanted to have a microgrid in a hilly region, and if it is a cold region, then how much resource, what kind of resource you have actually decides what the proportion that you are going to have, rather than the theoretical proportion that you are going to build. So basically, the environmental availability of the resources actually plays a more important role than what exactly that you can actually do. So I think trying to work on that kind of algorithms which can actually give a better mix and all is going to be of theoretical nature for this kind of systems. But let's say if you're actually trying to build a system for a military base where money is not the criteria, but you want to actually get every possible thing to be there, maybe yes, you can actually look at that kind of proportions to minimize the cost. Okay. Any other questions? I think I have answered all the 15 questions that are being posted in this chat box.
Yes, sir. Yes, sir. Thank you so much, sir. Thank you so much, sir. And thank you for such an excellent and informative session on realistic experimental test beds for micro and smart energy systems developed in IISc, and also for sharing the valuable inputs on how it can be made useful for different physical measurements and analysis, and also about the reconfigurability of substations, CT placement in substations, etc. I think all the participants really enjoyed the session, and almost 90% of the questions what they have posted, sir has already answered also. Because all the things whichever some repeated questions only we didn't post, remaining everything is posted, all the questions are as answered. I think everybody enjoyed the session. Once again, we express our gratitude for accepting our request, sir, to be an expert in this HTTP. Thank you so much, sir. Yes, sir. We know, you are extremely busy, like some Viva and other things you have to attend everything.
Yeah.
Thank you so much, sir.
Thank you. Thank you very much. Hope you all enjoyed. So my last comment is try to become developers, don't become users of technology. Thank you. Thank you very much.
Yeah. Thank you so much, sir. Yeah. So, dear participants, I think everybody knows about tomorrow's session. We have 3 sessions tomorrow, starting from 10 a.m. One minute. Yeah. So the morning session starts at 10 a.m. That is about intelligent control and its application microgrid by Satan sir from NIT Kurukshetra. Followed by that, we have next session from 11 a.m. That is about the effect of partial shading and interconnection schemes for PV systems by Dr. G. Sharavanalangu sir from NIT Trichy. And next, the third session for the day is starting by 3 p.m. It is about the understanding key critical measurement challenges and testing of next generation power electronic devices on gallium nitride and silicon carbide devices. It will be taken combinedly by Tektronix and NIT Silchar faculty. And all the 3 links are already shared in the YouTube link. And I think already it is mailed earlier to all the participants, and it is already available in the WhatsApp link also. So kindly go through that, and we can see that a lot of questions are coming related to the feedback. So feedback will be we will be providing the feedback link by the end of the session, and it will be provided with a time. So within that time, kindly try to submit the feedback. Okay. Thank you so much. Have a nice day. So we will be back tomorrow.